We did 2:1 multiplexer using K-map, and then we did 4:1 multiplexer. So multiplexer also, you remember, we did a two-part like decoder part, and then we did multiplexer where we have a like and or basically sum of products form and plus decoder make a multiplexer. Okay,
Yeah.
so today we will do a multiplexer using the VHDL code. Okay, currently we use using gate level code, gate level like writing the gate level code, and now we will write the behavioral code, which is like using the VHDL construct to create a mux. Okay,
Okay. So that
so
is from a library. We are going to import from library.
no, not improved from library. It's like a coding style will be there, which will create a mux,
Okay.
a coding style.
Okay.
Okay, so let's create a design source. And let's call it. We'll create 8:1 mux. Okay, using the behavioral code. Okay.
Okay.
So you remember we have so eight mux like we'll be having eight inputs, right?
Yeah.
So let's have eight inputs in arrays or vector. Okay. So in input mux as array. Okay. Since we are eight inputs, so we take eight. We are taking as a vector instead of having a separate eight inputs. Okay.
Yeah.
So to select eight inputs, we need 3-bit select, right? Select,
Mm, Three, I think.
yeah. To the power three is eight. Okay.
Mm.
Okay. Now there'll be one output out mux. So now, oh, this we cannot. This is a keyword. We cannot use this. Select is a keyword as ELA.
Okay.
So there's a like one way is there case statement. You would have like seen the case in the C also. So similarly, case is there in the VHDL. Okay. So we write case. First, you understand like there's two things are there: sequential statement and concurrent statement. So anything we write between the begin and end behavioral that will always execute together. So let's say I write a equal to 1 or b equal to 1, b equal to 1. So they will be executed together. Okay, they are any means there will be no difference between execution of both. So we cannot give a guarantee like a will be 1 first or b will be 1 first.
Mm.
They may be together or they may be slightly here and there. So you basically we should treat everything they are assigned together, which
Mm.
is there. Okay.
Yeah.
While in process, every sequential statement we write inside process. Okay, you remember in process. Okay, so every sequential statement will be written between process and any thing concurrent assignment can be written outside. Okay, so basically there is a two statement is there to write a mux. Basically, it's a case statement. So case is always sequential statement. Okay, so we should always use a process to write a case statement. So we do the case, and case for what? Case. input mux. Okay, input, because sorry, select, for each select, case select is, okay, and end case. Everything will be like ended, like end process, like that end case is there. Okay, and then code. Okay, so now we have to write the case. So for each case, so case when when 0 0. Okay, so therefore eight possibility values is there, right? Select 3-bit case is eight possible values. So when 0 0 0, then here is a statement. Okay, what we do when 0 0 1, what we do when 0 0 0 0, then what we do. Okay, when 1 0 0, we do something. So like that, we write all the possible things. Oh, sorry, we missed one. And the last is 7, right? So if we write, we can write 7. Okay, but one thing you understand, we cannot leave. This is like a. You remember I said like standard logic have different types of logic. It can have a 0 1 0 1, and no, don't care. Sorry, X, don't care. Uh,
Impedance
X,
values.
U value, X, Z value, and week 1, week 0, and weak impedance. Like the 9 different values are there. Okay. So currently we are using only 0 1 values, right?
Yeah.
Right. So there is other possible values out there, right? Which is like it can be 1x or 0 0, combination of anything, right? 9 possible values. Okay. This there possible values are there in the simulation. So we cannot. So it means like when these values are, what we should do. There is a possible values there, right? When all three beta don't care, what we should do that time. So to do that, we can write a default when others, basically when others means when other select values, we do something else. Okay, so this is a full case, like all possible combinations are written now. Okay, one more thing, like this can be a default one, right, because if we leave, if we are keeping extra thing, it means like we are doing something extra, one more, while we want only 8 possible combination, right? So
Yeah.
we instead of, so we can leave this. So for 7 or anything else, we will use a default. Okay. So when 0 0 is there, what we select, our output should select output mux should select. Basically, this two lines. You can write it in two lines also, and same line also, because yeah, it's not a problem. Okay. So currently, since one statement is there in each line, we can write in same line. So it took uniform. If let's say you can do many things in this case, in
Yeah.
this, when this, like how you write, right, in your C
Still.
code also, right,
Yeah.
you can do anything, right? So
Okay.
like that here also you can do anything, but this currently this is a mux, right? So we want to create a mux, so we'll do only one thing, that we just select one output. Okay, so what we select, output will be input mux. Okay, so like this.
Okay. So We are saying that zero to, I mean, if it is something like non-binary thing like high impedance or anything, we will do the that input max 7.
Yeah, 7. Yeah, with together with 7 because it's a mux, right? You remember hardware. So this hardware. So this is hardware, right? So there's only 7 possible inputs, right? So and 3 possible as 0. So whatever we do, we can have a default value of last selection, or you can create anything else default value. But since we want to create just only say 8 is to 1 mux, so we will have the last one as a default, or any one of 8 should be a default.
Okay, so any other combination will always give the that 7 in that case.
Yeah, that's 7. Yeah, that's 7. Yeah.
So why we do this? Because to avoid any kind of misbehavior because of that.
See, in real scenario, we will always write with the 1 0, right? Everything.
Yeah.
So whenever select is having some valid value, and then only we will treat the output as a valid, right?
Yes. Yes.
Otherwise, we will not treat as a valid output. So it does not matter whatever if select is high impedance or X or so we don't care what output comes, right? So
It's,
it can select either 7 or does not matter at all.
okay, so we are trying to avoid any kind of
So, so basically, we are trying to avoid extra hardware. Right? If let's say you have a extra selection, right? When S0 is something else. So basically, first of all, this high impedance into high impedance will not treat any it will not give you. It's just for simulation. Okay. High impedance is not for simulation. Like don't care and all is for simulation. So like even though you write a default value for last one, it will still create a AST 1 because there is only 8 valid values for the hardware possible, not for the simulation.
okay.
Okay. Even though if we write this 7 separate and when others for other condition, still it will create us 8 is to 1 mux only in the hardware because
So
there's
so this others is it like compulsory to use this others or I can avoid
yeah,
it?
yeah, others you cannot avoid. Others must become others you have to write.
Has to be part of that
Yeah,
case.
yeah, part of the case. This must be there, last one.
Okay.
And then so process must have a sensitivity value, right? It will enter the value, but when it should execute. So since there is a input, right? So we should write a uh, like some sensitivity list of process should have a sensitivity list and sensitivity list like select and then input marks. Output marks. Oh, output. Okay. So why we have a sensitivity list, right? So what will happen in the simulation if we have a sensitivity list? So what it does, like any change on the input, okay? If you don't if you don't give this, right, what will happen? It will keep enter here and doing this thing. Okay, keep doing this.
Okay.
So and keep doing this means like we don't want it, like it takes the simulations extra means cycles, right? So it
It
keep
will
doing
go
this.
in the loop, like in for loop.
Yeah. Keep doing so, and there's no wait statement, right? So it will keep doing this indefinitely. So so we should have a sensitivity list. There we don't need. You remember test bench we did not do this because test bench we have a wait, right? Uh, like it went enter inside, but there is a wait statement. It will wait until that time and it will execute. But for hardware, wait is not a synthesizable solution. So it cannot it cannot create any hardware using the wait statement. So here
So
we should
weight
wait on
is just for our understanding, right? Just for simulation
switch.
purpose.
Yeah, for the simulation purpose, but not for the hardware.
Okay.
For the hardware, it has to wait on something, right? Some change. So
Yes. Yeah.
wait will be the sensitivity list. It will wait for the sensitivity list change. So that list should have all the inputs in the used in the process. So what are all the inputs are there? Select is one input, and the input is one input marks, right? So what will happen? So any change on any of these value, both value, it will enter in the inside this and schedule that statement. So let's say select get changed. So it will go and do the select, and it will do the particular select and assign this value, and it will not assign because remember I was talking about block which I did not talk still blocking and non-blocking statement. Okay, so this is a sorry non-blocking. So it's a signal, right? So basically this assignment is scheduled. So it will schedule this assignment, and uh, when it comes out of the process, then it will assign this value. And again, any change is there on any input, it will do a schedule, and it comes out of the process and assign the value. So
Hmm.
let's say we can have this kind of thing also, right? We can have some intermediate signal. Let's say signal some, let's say XYZ. Okay, and we are writing instead of select, we are writing case on the XYZ, and while doing the writing, we are modifying for 0 itself. We are modifying the for XYZ assign something value, right? Dot dot dot. Okay, so what happened? Like we came in on the XYZ inside it, and we modify the XYZ itself. So what
Hmm.
will happen? So what will happen? Like
Will-
if we so so basically next time again it comes out and it sees the change on the XYZ, it comes again and execute it.
hmm. Yeah, the same value is assigned, so it is not going anywhere.
Yeah. So it will come and change basically. Basically, this is the case statement. Let's write the test bench and we can create what source, create simulation source. You can copy this test bench, right? It's a similar test bench. From here to here, you can copy so multiplexer 8:1. Remember, I have different signal name, right? Input marks. Okay. Then we have a select. Select is same. Okay. Then we have output marks. And now similarly, we have to update the component 8:1. The vector. And then select is there. Is 2-bit, 3-bit in output marks. Okay. Then count should be like how many bits? Now we have a 3-bit input and 8 bits or 11 bits, right? just all the possible values. Sorry, 11, but 10 down to 0. Then can have an input like 2 down to 0 or the input. So you can assign input marks as a 10 down to 3. Select is 2 down to 0. Okay. And this value will be 11 bits, right? So 211 and then count plus count equal to count plus 1. So we did not, we have to again use the unsigned.all library because we're using plus. So now we are done the test bench. I add this to one. But the mark set is to one name. Now it will come here. So now we have to make this as a top test bench to select it. Set as a top to so that this will run the simulation for this. You run it. This is select is 7. Input 7 is 1. 7 is 0. Select is 7, so 0, right? And then 0 is there, so 0 and 1 is 1, 0, 0. And then after that, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6 value is 1. So it's coming as 1, right?
Mhm.
Let's see how the elaboration hardware looks like using this. You see? Oh, we do not top model is different. Okay, that's fine. Go to source. You have to change the top. See, it's picked up a RTL mark by from using the case statement. So it will look like this. Understand? So so basically it understand like it's a case, okay, and then it will uh, basically it sees like it's a case statement. It's all the statements are assigned It's a full case because there is all the conditions are assigned. So it will pick up a parallel mux, which it will look like this. Okay. Mm. Let's see. We want
Okay,
to.
so one question. This in this output mux, we see 0 to 7 this input lines, right? So
Mm.
they actually given all the signals at once, and based on the selection, it will give the output.
Yeah, yeah.
I mean, but all of them are given at the same time to the input to
At the
that.
same time, yeah, yeah. It does not matter. Like you don't give all the same at the same time. It will what it will do. See, first of all, you understand it's a electrical characteristic, right? Everything is electrical. There is nothing happened together. Okay.
Hmm.
So if I give you some just a brief, like this is also means very important to understand. Okay. So in basically in hardware, what is there? You understand transistors are there, right?
Yeah.
So transistor with gates are formed with the transistors. Okay.
Yeah.
So some gate inside it will be like some transistors will be there. CMOS transistor, CMOS, or anything. Some transistors are there in each gate. So it means like, and what is a transistor? Transistor like uh, when you provide some input, output on the transistor will appear after some time because charge or the current move from here to here with in some time. It does not appear at the same time. It always takes charge move from
Hmm.
here to here and it takes some time to move. So
Hmm.
there's always a delta t basically involved in each gate. So each gate will be having some time for the transportation of input to the output. So
Hmm.
each gate will take some time.
The
Okay.
propagation. Yeah.
So so let's say let's you had a decoder, right? So you have a selector in, right?
Hmm. Hmm.
3-bit select. Okay. So let's say that's 2-bit select. Okay. So the four possibility was there, right? One was like direct AND gate, right? You remember, which
Hmm.
is one possibility, right?
Yeah.
Just three. Hmm? Then we had one like 0 0 possibility. Right? 0 0 possibility is what? Not
Yeah.
gate, right? And here also not gates.
Hmm.
So if I give here 1 1,
Hmm.
okay, and so let's say D also is there, right? Four possible inputs are there in, hmm?
Hmm.
And then this goes in 0 here and 4 here, right? Right, and then OR gate. If I try to see like I give all these inputs same time, let's say, okay,
Hmm.
and then and next input I give 0 0. I just change this. What will happen? What will happen? Do you think? First I given 1 1, and then next I given 0 0. So you see like uh, you get, let's say at the same, let's say this was 0, this was 0 0 0, right? Initially,
Hmm.
okay? And next time I made it 1 1 1 1. Okay. So
Okay.
what will happen? Like I made it 1 1 1 1, not 1 1 1. Yeah, yeah, 1 1 1 1. Okay. So what will happen? Uh, so when 1 1 was there, after some time, this takes some time, right?
Yeah.
So this will become 1, right?
Yeah.
And then this will be still 0, right? And then you get this one, so it will be selected this 0 here, and 0 will appear here, right?
Hmm. Yeah.
But next time you given this 1 1 0 0 and 1 1 same time. Okay, what will happen? Like when you given 0 0, this will immediately become 0, right? This will become 0.
Yeah.
Okay, this will also become 0. This was 0, right?
Yeah, that was 0. Yes.
So this take t time, this take t time, this take t time, and this take t time. Let's say so. Still at for some time, this is also 0, right?
Yeah.
And
Okay.
this is also 0, right?
Yeah.
Because for some time, because it still it, it has the 1 1 has not reached here,
Propagate that.
but
Okay.
0
Yeah.
0 has reached here,
Yeah.
right? So so nothing happens concurrent in the hardware, right? So that's why there's a like we have a timing. We call it timing in the hardware.
Okay.
Timing verification, or we say STS, static timing analysis. You have to analyze the timing whether everything is
So
beyond everything.
how do we analyze that? I mean, how do I know that this will take time or this will, I mean, this
So,
will take less time?
there's always a STA tool is there. Okay, we give some like some constraint to it. Constraint means like my design should work or from here to here, maximum transition like maximum time it should maximum time we say from here to here it should be some time, and minimum time from here to say we decide define some time, and then the STA will verify it whether the minimum and maximum time propagation is matching or not.
Okay.
So this kind of this is also like very like being a hardware engineer, you must know this and must
Mm.
able to analyze it.
So
Then
in
only
case,
you can design a good hardware.
okay, so this STA tool, in case, let's say it gives me unwanted results, like, for
Then
example,
you modify your design to pass
change,
this STA.
okay, to need to
Change your
change
design.
that.
Your design, yeah.
Okay.
Okay.
Mm.
So nothing. So that's what nothing happens parallel. In simulation, it will happen parallel. Simulation also nothing happens parallel. Simulation also have its own like race condition may occur, right?
So they take
If-
care of that automatically.
Yeah, yeah, yeah.
Mm.
It has to taken. It has to be taken care. Understand? And now, so this is like a parallel mux. We call it parallel mux.
Mm.
Okay, everything is happening parallel. And let's say there's also you have right. If else also you can do right. You remember?
If else, yeah, did we do if else? I don't remember.
No, no. I mean to say, can you know if means
Yeah, yeah, conditional statements.
conditional say you can in C all you can write the same thing with if else, right?
Yeah, yes,
Can you write in if you want to do the same behavior, you can write if else also, right?
yes,
And case also, right? We
yeah.
can do. Okay, we can do. Let's do it. We copy it. We comment it. Commented it. So let's do if else. Okay. So remove case. If else also is a sequencer state. If else also we have to write in the process always. We cannot write outside. Okay.
Okay,
Select equal to 0 0. Okay. If then we say okay then. You can write in two line also, one line also. That's not a problem. So if then this okay this output.
yeah,
Else if select equal to this. Okay. Then do this. Then so let's do quickly. It means like we are doing this to the line, right?
yeah, yes.
And and uh, and here we're writing then. Hmm, okay. What is the error? Oh, it's not equal, double equal. In C or Verilog we use double, right? Here.
Oh,
And you see, right, a case remove. So one thing is, right, we still missing others is not there, first of all.
okay.
In so we for default statement else, okay?
Yes, yeah.
And when else is there, we don't write then, okay?
Okay.
What is the problem? Then is oh, end if, sorry, I forgot. There's always a end if here in
And
the HDF, okay? So if also end, like how we end case, right? End case,
hmm.
there's end if also there. Filler is there. Filler.
the that the name, I think the process name. Name.
Okay. So now if we run the simulation, it will like remain same. No change will be there in the simulation. But hardware will be different.
Hmm. Hardware will be different.
Yeah, that's what I want to show you. Hardware will be different. Simulation is no different. Hardware functional output will be same, but it will implement different way. See, see what hardware is there.
It put that in the series. Looks like.
Series, yeah. So it will always have a 2:1 mux, and then it basically the priority encoder. I was saying like I'll tell you the priority encoder. So it what it does like is it has put on the priority on the first statement, which is like if let's say this is currently all the conditions are mutually exclusive, right? So
Yeah.
even though like there's no possible value if 0 0 is there, this is mutually exclusive to the 1 1 0 1 1 0 right? So there's no like still the result will same. Result will result between the parallel mux and this kind of implementation, the output will remain same. So, but if let's say the inputs are not mutually exclusive, then what will happen? Like it will give a priority to this, right?
Hmm.
So, so that's what I'm saying. Like the if else is always a priority mark, even though it can give you the same result, but it's a priority. So advantage of like it means like when we should use if else and when we should use case, we should know. We when we need to implement the if else, we should implement if else. When we need to implement the when else, sorry, case case statement, we should implement case. Okay. So when we should implement the case statement, when we know like all the like selections or all the like selections are like mutually exclusive, then we should implement the case statement. And
Mutually exclusive means they all are different. That's what you're saying.
yeah, the conditions will be always different, each.
Okay.
So we should always use the like
In case in that.
case. And if let's say two conditions, or we can have multiple conditions in and then like two conditions can be true at the same time, then we should implement and we let's say we want to have this one. We say as select 0, okay, is 0. Okay. Then only we want to this. We want to do this. Okay.
Hmm.
And let's say select is 0, 1, 0. Okay.
Hmm.
Okay. So you see like when the select is 0, when the select 0 is 0, then we want to execute this. But this is here also select is 0, right? Select 0 is 0 here also. But it will not execute this. It will execute this. So these two are not mutually exclusive. Why? Because this condition is here also true in this statement also, but it will not execute this one. It will execute this one.
They are two different values, right? Select zero is a zero, then
But select zeroth bit is 0 here, right?
select zero bit. Yeah, the LSB. Okay. Yeah.
Or we can say let's say select 1. Okay. Is it mutually exclusive? No. Why no, not execute both we can set sorry, both we can set together 0. We can set, right?
Hmm. Yeah.
Both values 0 together is possible, but still it will execute this one.
Hmm.
So this is called priority mux. So always the priority is given to the top selection line. So we should know when we want to implement the priority mux or when we want to implement the parallel mux.
So
Okay.
it will ignore the next line.
Not ignore. It will always execute when this is
Uh,
true.
yeah, I mean that will first line it will
So
do it.
let's analyze let's analyze in the semantics. What will happen? So we are telling like the top mux. So top is let's say S0. This is top first level mux. So if this is 0 or this is true, this line like this so we always connect the first statement. We always take irrespective of this is true or this is true or this is true or not. Irrespective of that, we always take this line from this mux. So that's the difference between hardware between the two case and if else. Okay. So now I want to just show you. I want to quickly show you the different coding style. Okay, we can write the same hardware with one more conditional statement is there. Let's comment it. It is when else. Okay, so we can write like output mux assign 000 when select is 0. So not 0, 0, just input mux 1, 0. Okay. This is what we are doing, right? Else, you can copy this. So this may be default statement. This is 0, 1, 0, 1, 0, 0, 0. So this you see, like we have written differently. When else, when else, when else, when else. Okay, but it will. This is also priority. So this will put priority on this. Okay. So this will also implement the same hardware, same simulation, but different style, different coding style. So this if else, if will be always written in the process, and when else should be always written outside of the process. Okay. We just reload. I'll not the simulation, but you can see the schematic. Schematic will remain same. Schematic does not change. Okay. And one more thing, I'll just let's comment this. Okay. I'll show you one parallel mux outside of the process. Okay. That is called with select. With with this one. Okay. Select. I'm saying right. Select is a keyword. So this select keyword is with here. Okay. With select output equal to mux 0 when 0, 0, 0, 0. Okay. Comma. Okay. So this kind of case statement, but written outside of the. And this last is always others. When this will be closed. Okay. This is not either multiple. This multiple. Okay. So this will implement. Okay. You have to change one. one. This will implement kind of case, which is parallel mux. And here also you have to give all others is important so that it will say it's a complete mux.
So we have to define the value for that like we did that for case.
Find the value means
in
you
the
see.
others. Yeah.
That's not means it will take 7 or any other value.
Okay, that is default.
Default value. It's others means default value. You see here default. You say last one default.
Hmm.
So just to recap today. So today what we learn? We learn like priority encoding, right?
Hmm.
We learn parallel mux and then priority encoding. And then what we learned, we try to see the semantic, like how it will implement the different hardware uh, using the different statements. So with select we learn with select and case statement is same thing. Only thing is like case is written inside the process and with select is written outside. So one you understand like I will say so one at disadvantage means you say you have you can have a question why we use this, why we can't use this, and we so why we have two doing same thing and we have two different means creating same hardware, why you have a question, right?
Yeah.
So question is means correct, answer is also there. Like here you see here you can assign only one statement, right? One out one with select you can assign only one assignment, right? One output you can only assign, right?
Yeah.
But here you can do many. With this selection you can assign multiple outputs. Like you can have multiple variable outputs. Basically, you can have output one, output two, output two, and some different some other statements also you can have here. Right, this is the advantage here while writing a case. You can do many things in the same case, right? You would have written C code, right? You will be doing
Yeah.
the same
Can
switch
write the
multiple statement. Yeah. But
conditions.
while with select you cannot write multiple. Only we can you can assign one variable or one signal only.
Hmm, okay, the output is only one for that.
Yeah, one and one per with select. Okay.
Hmm.
And same similarly here also, if else you can write many things, but you cannot write many things in when else. So there is a difference.
So, okay,
That,
so we set the if else and comparing that with this case statement,
mm,
that creates the different hardware, right? Case
yeah,
is
yeah.
creating parallel mux, and for this if else it is doing the uh,
Priority mix.
priority, having multiple small mux in the series.
Yeah, yeah. So
So,
one more thing I have to say. So once parallel mux is there, right? This is always uh, fast. Why fast? Because this is implementing parallel. So each path will be having almost similar delay,
okay,
except the decoder part. But while the if else is like sequential, right? Since a series. So if let's say we select the last output, select 7, so it has to go through so many mux, so many hardware, and it will reach very slow.
okay.
Input to output transition delay is very high. So this is inefficient way of writing. If you want to write a let's say parallel means as much as possible conditional statement is there. If you try to write a case, so it will be having a faster, I mean fast hardware basically.
Hmm, okay.
So that's what you should know when to write a case and when to write if else. You should have a prior imagination or prior thought before writing the code.
Okay. Yeah.
That's fine. And tomorrow, can we have a class tomorrow? Do you have holiday tomorrow?
No, tomorrow is a Monday.
Oh, okay. We have holiday, Easter holiday. Okay, that's fine. Then we can meet Wednesday only.
Yeah, okay. I also
So,
installing this the Vivado, so I think I can start practicing on that.
okay, okay. Yeah, sure. And let me know any questions are there when you're practicing.
Yeah, sure, sure.
And next time, like I think most of the combinational things we covered.
Hmm.
Next class we will start from the clock, registers, and all. We'll
Okay,
start from there.
so how much combination circuits I should know? I mean, Is it
It's
like
like we will cover like I think adder, multiplier, and so on. Many things are there. Like if you want, if I can say like you implemented adder, can you implement a multiplier
hmm, okay.
using the adder? So you should say yes, I can implement, and then you figure out how the how we do the multiplications.
Hmm, okay.
Right? You can you design. Can you try? If I say you have a full adder, you have a 4-bit adder. Can you use a 4-bit adder and implement a 4-bit multiplier using the 4-bit adder?
Hmm,
I think
okay.
you should be able to do.
Yeah, I will. So
You just don't write a code. Maybe just try the like how mathematics, like how we do multiplication.
okay. I mean, the K map. I will come up with
Not
the.
KMap. KMap is not needed. You already do the KMap job, right?
Okay.
KMap job is done. Right? What I said. I can you implement a 4-bit multiplier using a 4-bit adder
Using for.
related to the KMap job? You already implemented a. You remember when we did a 4-bit adder, we use a half adder and full adder. We already KMap is done at the leaf level, right? Leaf level. Like leaf cell was a half adder and full adder. There only we did the KMap. No need
Yes.
of at the full adder, a 4-bit adder. So can you and this is the one way of doing the hardware. So use a small elements and build a bigger hardware.
Okay. Yeah, I will take a look at that for
So
multiply.
don't write the code, just on the paper, pen paper, how it will look like. Means I think you should be able to do. It's just a pure mathematics.
Okay. The with the diagram, right?
Yeah, diagram. How
Hmm.
how many adders you will use, and how. You remember like we do our when we one digit we multiply when we shift right, and then we add zero at the less b.
Yeah.
That's how we do, right? Multiply, add, keep on shift and add.
Hmm. Yeah.
So you can try, and then once you try, I will guide you. Means not guide you. Once you have that, we can easily implement the hardware for the
Hmm.
multiple.
Okay. Okay. Sounds good.
Then
Yeah. See you. See you on Wednesday.
yeah,
Yeah,
okay.
thank
Bye.
you. Bye.